That's correct, Professor. Be the assistant, somebody do documents and stuff, watch the students, extra few points for me.
Don't do that next time.
Don't say that.
Yeah, so keep in mind, guys, that I'm also available for help if you wanna study, if you wanna schedule like one-on-one sessions. If we can't meet face-to-face, we can always do it online through Microsoft Teams, something like that. Just, we can also always schedule appointments. So if you need one-on-one help, don't be reluctant to ask.
Don't tell me twice. I will be there.
All right. Okay, any other comments or questions?
The review will be open after class today?
Yeah, we'll have this.
You also will be able to take it.
Yes.
We'll talk about it.
You called me, I had
Okay, so, let's go ahead and get started. So, we'll start chapter 5. First item we'll talk about is probability distributions. So this has a lot of loaded terms in it. It turns out that a probability distribution is a distribution that involves probabilities. And that sounds obvious, and it sounds like an absurd definition, but it has a lot of loaded terms in it that we've already talked about. So again, a probability distribution is a distribution that involves probabilities, so it's a distribution.
What's a distribution? Set of different values.
Okay, specifically what makes those different values a distribution?
So distribution is basically a percentage of a variable to a weight.
Okay, you're on the right track. So basically, it's a relationship between all values of a variable and how often those values occurs in the data set. And we've been able to represent how often all the values occurs in the data set. One way is with a table with 2 columns. For example, we talked about a grade distribution where your variable of interest might be a grade. And then within that column, we list all the possible values of that variable in the data set. When we first talked about this, for example, we listed all the numbers from 0 through 100. So those are all the possible values. And then on the second column, we list how often each one occurs in the data set. One way to list how often the values occurs is just a raw count. And we call that raw count a frequency. Another way to represent how often the values occurs in the data set is how. You guys remember? Instead of just counting up the raw occurrences, how else could we represent how often the values occurs?
Percentages?
Yeah, as a percent. So there's a frequency or percent, which we call a relative distribution, because a percent is just a relative difference. So those are 2 ways, different ways that we talked about how to represent how often all the different values of a certain variable occur in the data set. Today we'll talk about a 3rd way to represent how often the values occurs, and that's their probability. So let's review a little bit. Let's say that I have these numbers 1, 2, 3, and 4 cut out and placed into a hat. But each of the numbers occurs a different number of times. Let's say I first represent how often the values occurs as a frequency. So let's say the number 1 occurs 5 times, number 2 occurs 10 times, number 3 occurs 20 times, 50 times, and so let me get the numbers right. Okay. So instead of grades here, let's say that my variable represents the value of the number in the hat. So I have a hat, and I'm placing pieces of paper that cut out, each one numbered with a number. Happens to be 1 through 4, and the number 1 occurs 5 times, the number 2 occurs 15 times, and so on. So let's say that I repeatedly draw all the numbers out of the hat each time I make note of the number. And then at the end, after I've drawn out all the numbers, I take the average of all the ones that I've seen. So how would I find the average of all the numbers drawn? So this is a review.
So one would be, you multiply each of them and then you add the frequency. And then calculate the percentage by the division.
Yeah, very good. So really, this is just a weighted mean. So in the end, the number of ones that you end up drawing are 5 of them. So an average is really just add up all the numbers and divide by the number of numbers. So since in the end, you end up adding the number 1 5 times, adding the number 1 5 times is the same as saying 1 times 5. And then in the end, you're gonna add up the number 2 15 times, and adding the number 2 15 times is really saying 2 times 15. And we're gonna add the number 3 up 30 times, so 3 times 30. And we're gonna add the number 4 up 50 times. And then we wanna divide by the number of numbers. So what's the number of numbers here?
4.
Okay, so
No, sorry, so the frequency.
So basically, it's the number of pieces of paper you end up grabbing, right? So there's 100 pieces of paper here. If you add these all up, the second column. So the number of numbers turns out to be 100, found by adding the numbers in the second column. So that's a common mistake, is to look at the number of unique numbers and say that's the number of numbers, but really it's the number of occurrences of numbers, which is the sum of the second column. So this would be the average of all the numbers that you drew from the hat. And before you actually calculate it, let's say I played devil's advocate and said, well, why can't I add the numbers 1, 2, 3, and 4 and divide by 4? Why is that not the average?
They're weighted differently due to the frequency.
Yeah, that would only be the average if these 4 numbers were weighted the same. If they all occurred once, or if they all occurred twice, or if they all occurred the same number of times, then they're all weighted the same, in which case you could add up the 4 numbers and divide by 4. If they're not all weighted the same, like the number 1 occurs only 5 times, and number 4 is occurring 10 times as often, 50 times, in that case they're totally weighted differently, each of them, so you have to count for all the weights and do what we did here. So essentially it's just adding up all the numbers and divide by the number of numbers, just like any other average. Any questions so far? So this is basically a weighted mean, and we talked about this. So if you had added up the 4 numbers and divided by 4, you would have gotten 2.5, which ends up being the midpoint. So if you had added the 4 numbers and just divided by 4. But you would expect the correct average to be higher or lower or the same as 2.5.
Higher.
Higher what?
Because 3 and 4 are significantly more than 1 and 2.
Good, because you have a lot more numbers occurring over and over, the 3 and the 4, that are higher than the average of 2.5 if the numbers were weighted the same. You have a lot more occurrences of the 3 and the 4 that will push this average higher and higher towards those greater numbers. So you're going to expect an average that's greater than if the numbers were weighted the same. So the average would be higher than 2.5. So go ahead and punch this in and
3.25 or 13/4.
Okay, good. 3.25. So just like we expect, the real average is higher than the average if the numbers were weighted the same. Any questions? Okay, so again, this is review. This is if we were looking at a frequency distribution and finding the mean value of the variable. So let's say that instead of a frequency given to represent how often the values occurs, we're given a probability. So how do we convert each of these numbers into probabilities?
Divide each frequency by the total number of frequencies?
Yeah, it's basically converting to a percentage of occurrence, right? Because this number 1 is occurring 5 times out of the total 100 times. So it's really 5 divided by the total, or 100. So the probability here would just be the number 1 occurs 5% of the time, or what probability point okay. So same thing with the other numbers. So if you were asked to find the mean in this case, it should be exactly the same mean as for the case of a frequency distribution, where you were given how often the values occur as frequencies. But let's say you were only given the first and the third column, the value of the number and the probability of occurrence. So again, if I ask you to find the mean should be exactly the same as 3.25. So let's talk about how to find the mean if you're given a probability distribution. So essentially, before what we did was we multiplied the value of the number times the frequency, and we just summed them all up, and then we divided by the sum of the second column. So mathematically, this is exactly the same thing. So to find this mean, we're going to take the sum of the products of all the rows, and then divide by the sum of the probabilities. So we're going to do exactly the same thing. And then we'll divide by the sum of the probabilities. And this sum ends up being what?
1.
1. Good. And it turns out that that's not a coincidence. If you look at all values that are possible for a certain variable, and you look at the sum of all the probabilities, that sum will always be 1, because it represents the entire event space, 100%. So if you add up all the probabilities of all the possible values of a variable, you're always going to get 100% or 1. So go ahead and try punching that in. The top part divided by 1. Okay, good. So you notice you get the exact same answer as before, and we should be getting the same answer. It's what we expect. Because regardless of how often the values occurs, how they're given, the relative weights are still the same. Like the 2 here shows up 3 times as often as the 1, whether it's being presented as a frequency or whether it's being presented as a probability. So the relative weights are the same in both cases, so therefore the mean of the value you pick out of the hat should also be the same. It's like we expect. So if you're given a probability distribution instead of a frequency distribution, the way you find the weighted mean is the same. Find the sum of the products of all the rows, and then divide by the sum of the second row, the sum of the probabilities. It turns out that if you have a probability distribution, where how often the values occurs is given to you as a probability, then the sum will always be 1. And you know that a number divided by 1 is always itself. So that further simplifies it because you can ignore this denominator. Because you know that in a probability distribution, this denominator will always be 1. Any questions? Okay, so let's generalize what we just said. If you have a probability distribution, you're trying to find the mean of a probability distribution. But when we say the mean of a probability distribution, what we really mean is the average, but the average value of this x variable. So the average value of the variable in the probability distribution. And so let's go ahead and come up with a formula together. So again, the formula we use for this example is this top one here. And so if you look at the first term here, you have 1 times 0.05. And the 1 here is an example of so the 1 is an example of the first x variable, and the 0.05 is an example of the first probability. So P1, and so on. So this is x1, P1, and same thing for the next term. This 2 is an example of the second x, and the 0.15 is an example of the next probability, and so on. So the entire numerator is the sum of the products of the rows, where each row's product is its x value times its probability. So you just sum up each x times each probability. So if we were to generalize that, that'll be the sum. Remember, a summation is notated by this Greek symbol, sigma, and this is sum up all x times p's, or all p times x. Remember, when we multiply, it doesn't matter the order. But the convention is to list well, I'll leave it as xp. So sum up all x times p, and we're going to specify that by saying p of x, the probability of that x. And we know that in probability distribution, when we divide by the total, we end up dividing by 1, so dividing by 1 is itself, so you can ignore that. So in probability distribution, to find the mean, we ignore the denominator. Any questions? Okay. So let's do an example. Let's say that after the semester is over, we decide to start a business together. We can't get enough of each other. And so let's say that the business we decide to start is a life insurance company. life insurance works is that you have paying customers that pay you a certain premium. And let's say the premium is $101 per year. And the way that life insurance works is that you have these paying customers that are paying you $101 a year each. And if they happen to pass away before the year is over, then we owe their family $1 million. But most of the time, that's not going to happen. And most of the time, we're just going to collect the $101 from each customer. And then once in a while, if they happen to pass away, then we owe their family $1 million. So the probability, let's say the payout, if they were to pass away, is $1 million. But the probability that we end up having to pay out $1 million is only 1 in 10,000. So the probability that someone passes away is 1 in 10,000. So the question ultimately is, should we be going into this business? Meaning, what is the average amount of money we can expect to make per year, per customer? So the question is, what is the average profit per customer per year? Okay, any ideas on how to approach this?
Question first, how many customers do we have?
Okay, so the comment is, shouldn't it depend on the number of customers? Well, in the question it says per customer, so regardless of how many customers you have, we're implying that we divide out by the number of total customers we have. And the average should be the same, regardless of whether we have 100 customers or 20,000 customers, because we're dividing out by the number of customers. Okay, good. So any other suggestions? You guys think it's a good idea to go to business together?
No, not on this one whatsoever. I mean, the VA already thinks I'm 93% dead, right? So life insurance
Okay.
period is horrible, but I'm looking at this and it just doesn't make sense. So each person is paying $101 per year. There's 1 in 10,000 chance they'll die. So if I have 10,000 customers multiplied by 101, it gets a figure, and if one of them dies, I'm losing the majority of that to pay out that one family. So God help us all if they have 2 of them die, because now I'm in the hole.
Okay.
I'm just trying to figure out how to quantitatively put that on paper. So it should be,
Okay, so you're right. If you only had a smallish number of customers, like 10,000, then you could actually calculate the numbers just on 10,000, and you're right that if one customer dies, then you're in the hole already. But what if you had a large number of customers? What if you had 1 million customers? Then the idea would be the same, calculate your profit on 1 million customers, but let's try to generalize that. So let's say that basically we're asked to find this average profit, this average value here, where the value corresponds to profit per customer per year. So just like before when we talked about weighted mean, like when we talked about your average GPA, for example, where each grade that you get is weighted differently based on the number of credits that you take in the class. So it's basically the same idea here. You're trying to find the average of this value where the profit is weighted accordingly to what actually ends up happening per customer. So let's generalize this. So we're going to construct a probability distribution given as a table of two columns, where the first column will be your variable of interest. And your variable of interest is whatever it is you're trying to find the average of, which in this case is the profit per customer per year. So your variable here is whatever you're trying to find the average of, which is profit per customer per year. So that's the variable you're trying to find the average of. And then on the second column, you're gonna list the probability of that variable for all its different values. So per customer per year, what are all the different values of the profit that could happen for that customer? Or let's back up a little bit. What are all the possible life scenarios that could happen for that customer? That would influence how much we pay out.
So if they die, you get, we have to pay them $1 million, and, maybe they lost their job and they're only gonna pay 6 months and you're not getting that whole year for 101, so now you got, 52.
Oh, okay, good. So let's just keep it simple and not worry about those edge cases or the situations where we only have a partial payout. So let's say that either what could happen is that they live or they pass away. I'm just gonna write that for short.
So you either get 101 bucks or the family gets $1 million.
Okay, good. So for each customer, either one of these two things happens that would influence our payout to them. So if they live, then we keep the full $1 million, or we keep the full $101. So that means in terms of the profit that we get, we make the full $101. So let's emphasize that with a positive sign. And what's the probability of that situation happening?
1 in 10,000.
Yeah, 1 in 10,000.
No. It's not 1 in 10,000 for them to live, it's.
Oh, that's right.
Quad 9 over 10,000.
Yeah, so the probability of them dying is 1 in 10,000, but the probability of them living is what's left over from that. So 1 minus 1 in 10,000, which is 9,999 divided by 10,000. So almost 100% of the time, they're gonna live and we're gonna be able to keep the $101 payment. Okay, so let's do the situation where they pass away. How much money would we make or lose from them?
We lose $1 million.
Okay, great. So we lose $1 million. So this will be negative $1 million. So because we're talking about the profit is what we bring in minus what we have spent. So it turns out that we don't lose the full $1 million technically, because earlier on in the year, they paid us $101. So technically speaking, because we're talking about profit, it's negative $1 million plus the $101. So we don't lose the full $1 million. Any questions? Okay, so what's the probability of that happening?
1 in 10,000.
Yeah, 1 in 10,000. So basically we have a probability distribution, like we talked about in the previous example, and we're trying to find the average value of this profit per customer, the average value of this X variable. So just like before, each X variable is weighted with a certain probability. So basically this just reduces down to finding the mean value of this probability distribution. And the mean value of probability distribution is given by the formula we just talked about, which is the sum of each X times P of X. So basically each X multiply by its probability and then add the next X times its probability. So go ahead and calculate that.
living going all the way across is 100.9899. For dying, your million minus 101 divided by 1 in 10,000. Or multiplied by 1 in 10,000 is 91.98.
Okay, so when you find this total mean, what do you get? So sum up the product of each row.
Looking for the second one?
Just the value of this mean. So find the product of the first row, whatever that number is, and then the product of the second row, whatever that number is, and then add the two.
Oh, okay. It's like 200.
Okay, it should be lower, try again. Okay, so I heard someone get 1, so it sounds like it should be 1. You guys got that? Okay, let's do it step by step. If you do the product of the first row, multiply these two numbers, what do you get?
You get 100.9899.
Okay, good. So basically, you're taking almost 100% of this number, 101. So it should be a number that's very close to 101. Like you said, it should be 100.9 something, right? So exactly what is it?
100.9899.
Okay. So that's the product of the first two numbers. What about the product of the second two numbers?
It's 99.99.
But the thing is, you notice that it's signed, right? So this first number, if you take negative a million plus offset it by the small positive number, it should be a negative number.
That's what I messed up.
So you have this negative number times a small number, so you should be getting negative 99.99.
And that's where you got 1.
Yeah.
No, that checks.
So add these two numbers and you'll get 1. Okay, so let's talk about the meaning of this. This number 1 represents the average value of this variable, which represents the average profit per customer per year. So for each year, for each customer, you're gonna make an average of $1 per customer. So, is that good for business?
No.
No.
That's terrible.
Okay, it might not be as bad as it sounds, because that means that for each customer, you're making it $1. So if you had 1 million customers, how much would you be making on average?
$1 million.
$1 million.
Okay, so as long as the number is positive, that's good business. Because if it was negative, that means we're losing
Sure.
money.
Yes. And the bigger the positive number, the better.
Right.
But the point is that this isn't as bad as it might first seem, because this is the amount that you make on average per customer. But the more customers you have, you just multiply by that fixed number. So if you had 10 million customers, you'd be making a total profit of $10 million. Any questions? Okay. Let's do another example. Let's talk about the lottery. So, most states in the US have a lottery where they sell tickets, and if the number that they draw once or a couple times a week matches the number that you bought, ticket that you bought, then you win a big prize. And so, usually lotteries are funded by the government in order to make money for education, presumably. And so, let's talk about some of the numbers. Let's say that each ticket costs $1. And let's say that if you win $7 million. And the probability of winning is 1 in 13 million. So this probability, in this case, is given to you. If it weren't given to you, based on what we did in chapter 4, you could easily calculate this probability of a winning lottery ticket based on how many possibilities there were, how many numbers you could choose from the ticket, and so forth. So this probability is easily calculated. So the question is, what is the average amount of money that the government can expect to bring in for each lottery ticket? So what is So sometimes you'll see the question phrased as expected value. So expected is really just another way of saying average. And expected value is another way of saying the average profit. So when a question is being asked for average profit or expected value, usually the question needs to be clear as to who the profit is relative towards. So is this average profit for the customer or the average profit for the other end, the government? So in this example, I'm going to be explicit and say average profit from the standpoint of the government. So how much money can the government expect to make for each ticket? So we're gonna set this up the same way. So again, the quantity we're trying to find the average of, that'll be the variable of our probability distribution. So we're trying to find the average profit, so per ticket, so that quantity will be the variable in our probability distribution. So the profit per ticket and then on the other column, it'll be the probability that that variable takes on all of its possible values. So then let's look at the first column, the profit per ticket. So each ticket can have how many possibilities in terms of how it affects the profit for that ticket?
Win or lose?
Yeah, win or lose. So either it's a winning ticket or it's a losing ticket. So if it's a winning ticket, then what's the value of this variable that represents the profit the government makes per ticket?
1 minus 7 million.
Yeah, so if it's a winning ticket, the government made $1 when you bought the ticket, but then it's gonna lose 7 million. So it loses a net of negative $6,999,999. And then what's the probability of that happening?
1 in 13 million.
Yep, 1 in 13 million. And then if it's a losing ticket, then the government makes how much?
$1.
Okay, it makes $1 for that ticket. And then what's the probability of that happening?
12,999,999.
Yep. Okay, and so to find the average value of this X variable that represents the profit per ticket, to find that average, we would find the average value of our probability distribution. So just like before, so the mean will be the sum of each X times P of X. So multiply the numbers in each row and then add them all together.
$1.538.
Okay, so this is a great example. So if you had gotten this number, what it would represent is the average profit that the government makes per ticket. So if the government only sells each ticket for $1, can it make $1.50 per ticket if once in a while it has to pay out $13 million or $7 million? So in other words, does it make sense for the government to make on average $1.50 per ticket if it's only selling each ticket for $1?
No.
No, it needs to make, it ends up not being able to make the full $1 per ticket because once in a while, it's paying out the $7 million. So whatever answer we get, we expect that it needs to be less than $1. So, but this was good to talk about. Let's try it again. Make sure that you're accounting for the signs too.
46 cents.
Yeah, I've got the same thing.
Okay, good. So you should be getting 46 cents, which represents the average profit that the government makes per ticket. It doesn't make the full $1 per ticket, it makes 46 cents per ticket on average. Any questions? So again, if the government sells lots of tickets, if it sells 10 million tickets, it's gonna make 10 million times 46 cents a ticket. Any questions? Okay, so another thing I wanted to talk about is to find this mean. We talked about the formula to find the mean, which is to add up the product of all the rows. So another way that you can find the mean is just like with the weighted mean before, you should be able to use your calculator just to enter in these columns, and then the calculator will internally calculate the mean of this probability distribution for you using that formula and give you the mean. So you should be comfortable just being able to enter in these columns in your calculator and have the calculator give you the mean. And so again, every calculator is a little bit different, but the way that you found the weighted mean from before we talked about probability distributions, it should be the same way. And if you have questions about that, you see it. let's talk about another example. Let's say that you have a sweepstakes that you were playing, where let's say it costs $3 per ticket to play. Now let's say that if you were to win, you'd win one of several prizes. So if you win, so you could either win $1,000, the probability of that is 1 in 10,000. Or you could win $1 million, where the probability is 1 in 10 million. So ultimately the question is, how much money should you expect to win or lose per ticket every time you play? So, in other words, what is the expected value per ticket? But here's the perspective for profit is on you, the customer. So, in both of the previous examples, when we talked about expected value, basically we set up a probability distribution table, and then we multiplied each row together, and then we summed those all up. So the question is, essentially it looks like we have a probability distribution here. So can you just multiply these two rows together, and then add these two up? Would that give you the correct expected value per ticket?
They're both if you win, but they're weighted differently.
Okay, good. So they're weighted differently, but that's kind of the point, is that to take the different weights into consideration when you multiply the rows. So after you multiply the rows together and add them up, would that give you the correct expected value per ticket?
You still have to factor in the $3 that you had to pay to play.
Okay, very good. So I tried to trick you. And so there's so remember in a probability distribution, we said that if you sum up all the probabilities, they have to add up to 1. Because the premise is that you're accounting for all the possibilities of this x variable. And if you account for all the possibilities, then the probabilities will add up to 1. But here, as a sanity check, if you're to add up all the probabilities, they're not adding to 1. And that tells you that there are cases that are left out from this variable. And so if you had accounted for all the cases, then the probability should add up to 1. So what cases are we missing?
If you lose.
Yeah, so we're only accounting for the case if you win, but we're not accounting for huge possibilities that we could lose. So we need to account for that. So if we lose, then how much are we losing per ticket?
$3?
Yeah, we're losing the full $3 if we lose. And what's the probability of that happening?
For $1,000 is quad 9, and for the $1 million, it's 999,999 over.
Well, what's the probability that we just lose $3? So you're on the right track. How do we account for those two different probabilities that you just mentioned? How do we condense that into one number?
You multiply them?
Okay, why would we multiply instead of?
Because you could, you multiply if it's an or, because you could either win 1,000 or win 1 million, or you could lose both actually.
Good, so an easier way to think about it is you know that all the possibilities have to sum up to 100% or 1.
Right.
So this is the only other missing case. So you know that these three numbers have to add up to 1. So this missing number has to be 1 minus the sum of the previous two numbers.
Okay.
So this has to be 1 minus whatever the sum of these two are, and I'm just going to use this notation.
You make the denominator equivalent, make that 10,000 equivalent to the 10 million.
Okay, good. So when you find the sum, either you can use your calculator, or if you're doing it by hand, then you combine the fractions by using a common denominator. But if you were to use a calculator, 1 minus the sum of these two, what probability do you end up getting?
0.999899.
So 0.998999, so a number very close to 100%. Because the probability that we'll lose the full $3 for each ticket is virtually 100%.
There's 39 before the 8.
Oh, 3 nines for 48, thanks.
I didn't look it up, sorry.
No problem.
Okay, so now we're asked to find the expected value per ticket. So we're gonna do the same thing that we did before. We're gonna multiply each row together and then add those all up. Or you can use the mean feature of your calculator, enter in these two columns, and see what you get for the mean. What do you guys get?
2.8.
Okay, that sounds about right. Unless you guys get that. Okay, so what does this mean? This means that every time you play the sweepstakes, on average, you're gonna lose almost the full $3 per ticket. You're gonna lose $2.80. Another way of thinking about that is if you play repeatedly, like you play, for example, if you played 1,000,000 times, or if there's 1,000,000 customers that played 1,000,000 times each, or played once each, then if you took the average of everything that they lost or won per ticket, then that average would come out to be $2.80. Because most of the time they're gonna lose. Once in a blue moon, they might win, but it happens very infrequently. Any questions? All right. So we talked about how to find the mean of a probability distribution. So if you had a probability distribution, let's go back to the hat, numbers in a hat example. So x here represents the number in hat. And let's say again you had that same probability distribution from before. We talked about how to find the mean. So the mean is basically the average value of each value is weighted this way. So it would be the sum of each x and x. So remember, we have a bunch of numbers. Like basically that's what this is, a bunch of numbers where each number just happens to be weighted a certain way. So if you have a bunch of numbers, there's usually two measurements of interest. One is finding the center of those numbers, or the most typical number, measured with the average. And another measurement of interest is some measure of variation, how the numbers are spread out. So we also are interested in the standard deviation, because that's the most common measurement of variation. And so remember, the standard deviation is the square root of the variance. So it's the square root of the variance, which is the average squared distance from the mean. So if you take each number, x, you subtract out the mean, and you square it, that's the square distance of each number from the mean. But we want the average square distance from the mean. So we're gonna take the sum of each value and then weight it accordingly. So this gives us the average square, this gives us the square root of the average square distance from the mean, which is approximately the average distance from the mean. So remember, when we calculated the mean of these numbers, we said that it wasn't going to be exactly 2.5 because there's a lot of numbers weighted higher. So it turns out that the average ended up being 3.25. So we want to know if we're to list out all these numbers in their respective probabilities or weights, and we take each number and we subtract the mean, what is the approximate average distance of each number from the mean? And that's the standard deviation. So let's do both. Let's calculate the standard deviation by hand, and then I also want you to use that standard deviation feature on your calculator, where you can just enter in these two columns and see that you get the same number. So we'll first calculate this by hand. We're gonna take the square root of the sum of each x minus the mean squared times its respective probability for that x. So the first x will be 1, and then the mean we calculated before to be 3.25. So it'll be 1 minus 3.25. We're gonna square that, or we're gonna multiply that result by the probability of that value, which is 0.05. So this is the first term that we end up adding for that first row. Now we're gonna do the same thing for the subsequent remaining rows. So now we're gonna add, put the rows down here. So we're gonna add 2 minus 3.25, square that, multiply by its respective probability for that value of x, 0.15. Add that to the next. And then last row. So we want to add those all up and then take the square root of everything. So go ahead and try that. Let's know what you get. The data being sidestepped in statistics.
Negative 0.27%.
Okay, so remember, we're taking the square root, so we can't take the square root of a negative number, so it's gonna have to be positive.
I got 1.874.
And that's what I have.
So make sure that you can get this number by hand, or if not, also, there's that standard deviation function on your calculator there in the 2 columns. So what does this number represent? It represents approximately the average distance of each of the numbers from the mean. So the average spread of the numbers from each other, or from the mean, is approximately 0.88. Any questions?
Yeah, that makes way more sense.
Okay, good.
It helps if you actually do it in order instead of what I did, so.
Now,
I was going individually and adding them up, and I didn't square anything out of it for the room. I'm like, oh, yeah, you missed the first box.
okay. So then this is the answer that you get by hand, and then make sure that if you use the standard deviation feature on your calculator, by entering the two columns, that you're also getting the same number. So now that you know that every time you use that function on your calculator, that calculator is just internally using this formula. Okay, so we actually have a bit of time. This was the material I was thinking about just going through today, but we have a good bit of time. So we'll actually start the material that we have planned for tomorrow. And that's actually good because the material for tomorrow is actually conceptually pretty dense. And objectively speaking, it's one of the more difficult concepts for the entire semester. So it's good that we have some breathing room to start today. So the next concept we're going to talk about in chapter 5, it's called the binomial probability. So let's build up to this from what we've already talked about in the past. So let's say that in this example, I tell you that you're taking a multiple choice test. And let's say there's 5 questions and 4 choices per question. So the first related question is, if you were randomly guess on all 5 questions, then what's the probability that you'll get the first 2 questions correct and the last 3 questions wrong? So this should be reviewed. Any suggestions?
So that's gonna be more on the given statement. So if your 1 and 2 are correct and 3, 4, and 5 are wrong.
So good. You are trying to find a probability with events going by and. You want the first 2 questions to be correct and the last 3 questions to be wrong. So which rule addresses probabilities with and? Multiplication rule, good. So, using the multiplication rule, we want the probability that the first question by itself is, so basically, this probability we're trying to find, let's notate it this way, where C is getting a question correct, and W is getting a question wrong. So we want the first two to be correct, the last two to be wrong. So we're gonna multiply these individual probabilities together. So the probability of getting the first question correct is what? So 1 out of 4, there's 4 choices per question. So probability of getting one question correct is 1 out of 4, and now we just multiply the probabilities together. Next question correct is 1 out of 4. What's the probability of getting a question wrong?
3 out of 4.
Yeah, 3 out of 4. And getting a question correct or wrong are all independent of each other. So whether you get the first question correct or not, getting the second question correct is always 1 out of 4. So that's why we don't have to worry about conditional probabilities here, even though originally that's what the multiplication rule calls for. But getting a question correct or wrong are all independent events. So these probabilities are all consistently, if you get a question correct, it's 1/4. If you get a question incorrect, the probability is 3/4 consistent. So 1/4 is being multiplied twice. So another way of saying that is 1/4 raised to the 2 power. And 3/4 is getting multiplied 3 times. So another way of saying that is 3/4 cubed. Any questions? Okay, so this is the probability of getting the first 2 questions correct and the last 3 questions wrong. This is just the multiplication rule. This is a review from last time. So let's say that the previous question was modified and we were being asked, what's the probability? And instead of just getting the first 2 questions correct and the last 3 wrong, we're asking what's the probability of getting any 2 questions correct and the remaining 3 are wrong. So another way to say that is the probability of getting exactly 2 questions out of 5 correct. So let's just talk intuition. This probability, the answer should be the same as before, or higher or lower.
It'll probably be higher because it's not exactly the first 2, it's any 2, and you're randomly guessing, so it will probably be higher.
Okay, very good. Because the probability measures the likelihood or the chances of something occurring. And in the previous case, you want the chances of this exact situation occurring, which is the first 2 are correct and the last 3 are wrong. But here, we're actually allowing for more possibilities. Instead of just this probability, what other situation would fit this description of exactly 2 correct?
Getting the first 3 wrong and the last 2 correct?
Yeah. So this is another situation that fits that description. What's another situation that fits the description?
Getting the first and last correct?
Yeah, getting the first and last correct and everything else in between is wrong. So already we have 3. So because there are more situations that could occur that fit the description, the likelihood of any of these happening should be higher than the likelihood of just this one thing happening. So now what we're going to talk about is exactly how many of these situations are there that fit this description. So in order to help us think about this, what we're going to do is these positions representing the test questions themselves, we're going to label questions 1, 2, 3, 4, and 5. And for each situation, we're going to just record the questions that we get correct. So in the first case, we got questions 1 and 2 correct. So that'll be notated as 1, 2 to indicate that we got questions 1 and 2 correct. And any number that's not listed, 3, 4, and 5, that implies that we got those questions wrong. So using that notation, how would we represent the second event?
4, 5.
Yeah, 4, 5, meaning that we got questions 4 or 5 correct only. and then everything else is wrong. And then the next one?
1,
Yeah,
5.
1, 5, good.
Yeah,
Okay.
Wouldn't this be the same as doing like the factorial, five factorial over 2 factorial, 3 factorial, because you need 2 correct and 3 wrong.
Okay, good, so let's build up to that. So before we talk about how to actually find it mathematically, let's list them all out by hand.
Okay.
So, what's another combination or another group of two numbers that represent getting those two questions correct?
So,
1, 3, good, is 1. That means you got the first and third question right.
yeah, 1, 4.
1, 4. 2, 3, good.
2, 4.
2, 4, good.
3, 5.
3, 4. 2, 5.
Okay, 2, 5, good. Anything else?
2, 1. No, so that's going to 1, 2.
Okay, that's a good example. So 2, 1.
It's the same.
Yeah. So the question is, if you got questions 2 and 1 correct, is that the same as getting questions 1 and 2 correct?
Yes.
Yeah. So in that case, we say order doesn't matter, and we only care about the identity of the questions we get correct. So this is actually included in this case. Good. So anything else? Okay, very good. So it turns out that that's it, and the reason why that's it is because there should only be 10 possibilities. And the way that we know there's 10 possibilities is that we can compute the total number mathematically. And so each of these possibilities ends up having how many things in it? Ends up having 2 things in it, 2 objects. So then we're going to list out these 2 as representing the total number of objects or categories for each possibilities. So the first category represents the first question you end up getting correct, the first question number. So how many options of question numbers are there to get correct for the first question? Yeah, there's 5. And then once you get that question right, how many options are there for the second question you get correct?
4.
Yeah, 4. And then if you just multiply this, then you are implying that the order of these 2 within each possibility matters. It gets counted. But you don't want the order to get counted, so we're going to divide by 2 factorial. So this ends up being 20 divided by 2 times 1, or 20 divided by 2, which is 10. Another way to think about it is 5 times 4 is by definition 5 per meet 2. You start with 5, you multiply down 1 at a time until you have 2 numbers total, and then you're dividing by 2 factorial. So you have this permutation divided by this factorial, where these 2 are the same, and by definition this is a combination. So this is a 5 choose 2, a combination 2. Okay, so there should be 10 total, and that's given by 5C2. So that's for E2. Any questions? Okay, so you have this 10. Okay, so here we got the 10 by keeping track of the questions that you got correct. And then the numbers that we didn't list, that's implied to be the questions that we got wrong. But what if we had kept track for each possibility of the question we got wrong instead? So instead of keeping track of these 2 questions you got right, 1 and 2, the questions we're getting wrong are what's left over, which is 3, 4, 5. And let's say we did that for every possibility. So instead of getting questions 4 and 5 correct, we get which one's wrong? 1, 2, 3, and so forth. So 2, 3, 4. So if we had done that for every one of the 10 possibilities, then how many possibility should we be getting where we're keeping track of the 3 that we get wrong? How many of these should there be?
10.
Also 10, because there's a 1-to-1 correspondence, right? For each of the 10 that we're keeping track of the 2 questions correct, there's also only 1 possibility where we're getting 3 questions wrong. So for all of these 10, originally, there's also 10 where we're keeping track of the 3 questions we get wrong. So in the above case, this was 5 choose 2. But here, you can think of as how many ways are there for me to select 3 numbers from 5, where order doesn't matter with the 3 numbers. So this would be 5 choose 3. So either way, you're gonna get the same answer, 10. 5 choose 2 will be 10, 5 choose 3 will be 10. So it turns out that this is actually not even a coincidence. This can be generalized. So you notice that these are the same because these 2 numbers add up to be the original total of 5. So we can generalize that. If we had done 100 choose 40, that's going to be the same as 100 choose the second number, where the second number adds up with 40 to give 100. 60. So it turns out that if you punch in 100 and choose 40 into your calculator, that's exactly the same as 100 choose 60. And it's this same rationale.
So it almost makes you think of the complement part, this given that, the complement is still equal 1.
Mm-hmm. Okay, so based on that, if I ask you 20 choose 5, what's that the same as? 20 choose what?
15.
15, very good. And just to verify, you can punch that in your calculator, and you'll see that this is indeed true. Okay, questions? Okay, so going back to this, the total number of possibilities that you get by getting exactly 2 questions right out of 10, out of 5 questions, it will either be 5 choose 2 or 5 choose 3. They'll both give you 10 possibilities. So if you want exactly 2 correct, that means that you want the probability of any of these situations of occurring. The probability of either you get the first 2 questions right, or the last 2 questions right, or the first and the last, and so on, until you have a total of 10 things. So if you have a probability of events shown by or, which rule is that? Yeah, that's the addition rule. Okay. So let's review what the addition rule says. Addition rule says that if you have a probability with 2 events from by or, that will be equivalent to the probability of the first event plus probability of the second minus probability of the overlap between the events. So let's try it for this example. So the addition rule just generalizes the rule in terms of 2 events, just so we know the structure of that rule. But here in this case, we have a probability with lots of events run by or, so 10 events run by or, not just 2. But general principle is the same. So we're gonna add up the probability of each of the individual events and then subtract out any overlap. So if we look at the probability of just the first event, getting the first 2 questions right, what's that probability?
It's gonna be 1 out of 10.
Well, this is subtle. 1 out of 10 is only if all the events are equally weighted. But getting so in this case, we actually calculated this probability already, and what's that probability? So 1 out of 10 is only if all 10 events comprise the entire event space of these 5. and there's only 10 of them, in which case they're all equally weighted to be 1 out of 10. But if you have these 5 questions that you could either get correct or wrong, you actually have a lot of other events in the event space, and not just these 10. So that's why the probability isn't just 1 out of 10, but we calculated probability over here. Probability the first 2 questions are correct and the last 3 are wrong, and it was this probability, right? So each individual probability is 1/4 squared times 3/4 cubed. And that's the probability of just the first event, where you get the first 2 questions correct. What about the probability of the second event? Last 2 are correct.
The 3/4 cubed times 1/4 squared.
Yeah.
So it would be the same answer, but it's a different lineup, so to speak. I don't know.
Yeah, so in the first case, you want the first to be correct, and the second correct, and the third wrong, and so forth. So probability with and is multiplication rule. We ended up multiplying these 5 probabilities. In the second case, you still have probability with events run by and, so you still multiply the individual probabilities. So you're multiplying the same numbers but in a different order. But order and multiplication doesn't matter, so you'll get the same answer. So the second probability is still 1/4 squared times 3/4 raised to the 3rd power. So
every probability going down there is going to be the same if we're trying to get 2 right and 3 wrong.
very good. So each of these individual probabilities is still the same, 1/4 squared times 3/4 cubed. Same with this one, same answer. And how many of those same probabilities are we adding up?
10.
Yeah, 10 of them. Because based on what we said over here, we enumerated the 10. So we're adding this number up 10 times. So another way of saying that is 10 times this 1/4 times 3/4 cubed.
1/4 squared, though, right?
Yeah, 1/4 squared.
So you just put the whole thing in brackets and do the whole thing out to compute your answer, right?
Yep. So just multiply these 3 terms together, and that'll be your answer. Okay, so one last technicality is by the multiplication, or by the addition rule, which we ended up using here to add up the individual probabilities. Technically, we have to subtract out the overlap. So minus the probability of any of these events possibly occurring together on the same test. So is there any way on the same test where you get the first 2 questions correct, and at the same time, you get only the last 2 questions correct at the same time, on the same test? So on one test, you're gonna get only the first 2 questions correct and the last 3 questions wrong. And another test, and on the same test, you get the last 2 questions correct, the first 3 questions wrong. Is there any way for these 2 to happen on the same test? No. So we say that these events are disjoint from each other. They can never happen together. So because of that, this general probability that's in the addition rule, in this case, you can ignore it. Because these events are all independent, are all disjoint from each other. Another way of saying disjoint is mutually exclusive. They can't happen in the same event. So you can ignore this, and so in the end, this answer will just be this probability added up 10 times, or 10 times 1/4 squared times 3/4 cubed. So that'll be the answer. So that'll be, let's see. So the final answer will be 10 times 1/4 times squared times 3/4 cubed.
135 it's gonna give you 0.263, which is
Okay, good. So you notice that if you compare that answer to the first one, where you're getting the probability of exactly just the first 2 questions correct and the last 3 wrong, then that probability was just the 1/4 squared times 3/4 cubed, which is 0.0263. But this new answer is 10 times that. or 0.263 instead of 0.0263. So just like we expect, the answer to this probability of any 2 questions correct and the remaining 3 wrong is going to be a lot higher in probability than the previous answer. Because you're allowing for more possibilities. Any questions? Okay, so this was very conceptually dense. Next time we'll review what we talked about today. Okay, have a good day, guys.